Thank you, guys. Thank you. I appreciate this. Asha, where are you? Right there. Thanks. Okay, Linux on GPU. This is the. Now, some of you might have this reaction, like Linux on GPU. What? Maybe it's the opposite. The GPU on Linux. This sounds more like it, but. Yeah, let's just work it out throughout the hour. And before that, I'll just introduce myself. I joined NVIDIA 2010. Initially, I worked as a software engineer in the PhysX group. PhysX is a well-known simulation engine. And then I worked on many other things. These are just a subset of the things that I work on. Currently, I'm the site lead of the NVIDIA office in Yerevan and the director of technology at NVIDIA, but also still a software developer. So my past experiments related to the topic anyway include the emulation of a Game Boy. Now, I would like a show of hands who knows what Game Boy is. Okay, surprisingly, a lot of people. Diana didn't raise her hand because she's too young. This is, for those who don't know, this is a portable gaming console, a fairly desired one back in the 90s, at least within Russian youth. It was fairly expensive because it was portable. And the principle is really simple. You buy it, it's like a size of Tetris game, but you can change games by changing cartridges, which you buy separately. Now, the internals of the Game Boy is that it's based on a CPU that is a fairly weird mix of 8080 and Z80, running at around 4 megahertz. The exercise of emulating a game console is actually quite rewarding. I really do recommend it as a pet project. Emulating, I should say, something like a Game Boy is really not all that hard, but the reward comes when you get it just barely working. It shows some pixels, and now you have this choice of trying out hundreds and hundreds of games, cartridges, because there are images now in the internet that you can just download and play through your emulator and verify that it probably doesn't work, but that's the way you debug your implementation of the emulator. Now, obviously, now the slide says the Game Boy was running on GPU. And obviously, this is not the most applicable workload for a GPU. It's not really tailored to do this sort of things. The GPU, of course, is more tailored towards doing the same thing for a lot of, for large amounts of data. Now, Game Boy is a heavily divergent workload that GPUs really do not like, especially when you combine lots and lots of instances of this emulator to run on the same GPU at sort of the same pace. This was the end result. This is just a screenshot. Of course, there's a video that shows that I run here 16 by 8, so 128 instances of a Game Boy emulator, each having its own CPU, its own types of RAM that you need to emulate, its own, I wouldn't call it a GPU, but let's call it GPU, and each running its own cartridge, a game. Now, 128 is nothing. I was basically just limited by the screen space area to be able to even show that many. In the background, I could run 10, 15,000 of Game Boys, all together in parallel on a GPU. And why is that? Well, because so many years passed, right? I'm running it on a GPU that was released in 2021 or something, while Game Boy was released at the end of 80s. like 89, I believe, was the first year the very first Game Boy was released. So many years passed, and even though GPU is really not tailored to run this, it's still fast enough to do this. Is it useful to do this sort of thing? Probably not. When I've sent an email internally, just showing off, only RL, reinforcement learning people were interested because they actually do use games like Game Boy or Dendy or Sega to train certain reinforcement learning-based models, and their feedback was that it is actually beneficial to do this on GPU to avoid transferring the environment state between CPU and GPU, because they are used to emulate this, use normal CPU-based emulators and just move the data between CPU and GPU all the time. The learning actually could be faster in certain cases if you keep everything on GPU. But still, this is a niche case. In general, of course, it's not really a normal thing to do. So after that, this was like 2 years ago. After that, on a sort of back burner, I was thinking, what else can we do in this same direction? Can we do something even more weird, running something like, say, Linux? And so before diving into technicalities, I just wanted to address this elephant in the room, like why? Why to do this? Is there any benefit in this? And there are several reasons, I guess. The first reason is I just don't care if it makes any, if anyone can actually use it. It's still fun, so this is the main reason. It's like a bottle in a ship. It's useless, but it's nice to just look at it from different sides and talk about this. And also, I find doing exercises like this tends to be highly educational, because you know the goal. I just want to run Game Boy on Linux. I just want to run Game Boy on GPU. I just want to run Linux on GPU, or I just want to implement, say, a ray tracer with a finite speed of light. That's the other pet project that I've done previously. Is it useful? Is it scientific? No, but I find setting this sort of challenges is tends to be educational, because it tends to have a lot of these side quests that you need to cover, you need to understand, and this is the sort of thing that I'm going to talk about today as well, about these side quests. So, how do we want to run Linux on GPU? One might think that we could just compile Linux kernel and the software that we are going to run along with the kernel for a GPU. So we would use like a CUDA compiler and just use it to compile the Linux kernel. The problem with this approach is that it's monumentally hard. It's practically impossible, because obviously Linux developers do not target GPUs and CUDA as their environment to run Linux kernel on. So you would have to do everything yourself. The GPU, the actual processor, and VRAM that accompanies it are only in certain aspects alike to a normal machine for which Linux kernel was developed, and in a lot of other aspects it's totally different. So you would have to manually rewrite a lot of things. You would have to basically spend years, I think, at least, doing this, and still perhaps end up with nothing. So the other option is, of course, to just emulate it. And this is the option that I do. And so the way to do this is you emulate a sort of mini system that contains a CPU, some RAM, some input-output of your choice, And then you implement this all in my case in CUDA, but of course my recommendation, if you ever, by the way, if you ever attempt to do this on GPU, first do the reference implementation on CPU, because the debugging experience is going to be much, much nicer. And I assure you, you will have problems. So with Game Boy, in the past, I've done the CPU emulation all myself. It was not too difficult. It's a lot of just monkey programming. You go through all the instruction set and basically write the code to emulate it. This time around, because I had a kind of a bit harder goal to meet, I've decided to take an implementation for RISC-V emulator called SEMO. You can find it on GitHub. It's open source, and I decided to use that as a starting point because at that point it wasn't really interesting to me to implement a RISC-V emulator from the ground up, because in a way RISC-V is actually kind of simpler than these weird Xilinx 8080 hybrids by Sharp in the Game Boy. The instruction set is much more modern, simpler, and easier to implement. So I started by porting this code to CUDA. In a lot of cases, it's basically just marking functions for execution on GPU, but also kind of rewriting code in certain bits where, say, you cannot obviously do a syscall from a GPU code. So you would kind of arrange a buffer or a sort of ring of some sort to communicate with the necessary bits on the CPU. Now, how emulation works is, let me switch to the other mic. Am I still on? Yeah, I'm still audible. So the way this works is you have on the left your code that you run. In my case, it is a Linux kernel compiled for RISC-V architecture. And on the right, the emulator has this, typically, has this giant switch statement, which basically says, is the instruction that I'm about to execute a load byte, say, the first instruction there? No. Is it store byte? No. Is it BQZ? Yes. So we get into this block of code and we basically just implement the action of this instruction ourselves in the language of choice. C++, Python, doesn't matter. You just have this giant switch statement, what you do on each instruction, and you maintain, of course, the state of the machine, which is the register file, flags, interrupts, and all that. You just basically open a spec for the architecture that you are about to emulate, in my case RISC-V, and you just do what they say in code, and that's how you do emulation on a CPU. Now on GPU, it's kind of similar, except there is a nuance there that you typically, on consumer hardware anyway, you typically cannot just start executing a CUDA program on a GPU and forget about this. It cannot run for, say, 10 seconds on, say, Windows. The problem with this is WDDM model for the Windows driver. Basically, there is a hard limit of 2 seconds, I believe, that if you run any GPU workload, it could be related to graphics, to compute, whatever, the Windows operating system will just kill your kernel and it will stop working. However, there is an escape hatch, which is called TCC driver mode. It's available on Linux. It's also actually available on Windows, but only if you have a sort of prosumer hardware like Quadro or Tesla, when it was a thing. And in that case, you can avoid this limitation. But in my case, I'm that kind of guy. I'm running Windows, so I did have this limitation, and therefore, this is why I had to ask on CPU to run a kernel on a GPU, but only for a limited amount of instructions, to not get caught into this limit of 2 seconds. Now, how to run this on a GPU. I would like to ask for a show of hands, who knows what CUDA warp is? Only like 4 people, so I must explain what that is. So the way the GPU works is, they talk all the time about these CUDA threads and how you can run thousands and thousands of threads on a GPU. This is the case, but you ought to understand it on a deeper level to really be able to make some progress in GPU programming. The way this works is the machine, the GPU, combines threads in groups, and these groups are called warps or blocks, thread blocks, and the group size is 32, and it's deeply imbued in the hardware, meaning you cannot just make it, say, 50. It's 32 for a good reason, because the hardware is organized in such a way that all threads must, ideally, execute exactly the same instruction, but work obviously on a different piece of data. So if you say want to sum 2 vectors, 2 megabyte sized vectors, each thread will access its own element in each vector, A and B, and sum it into target location in vector C. That's how it works. So the thread ideally should, the warp should have non-divergent threads. I previously mentioned this term called divergence, and it might happen if your CUDA code, say, has if statements where a certain thread might depending on certain, conditions, can go either in one direction, in if direction, or in another direction, in else direction. If this happens different ways within a warp, this is bad for performance. And by the way, I find it funny, this asymmetry between our talks today. Ashot was talking about how to make things fast. I'm talking about how to make things really slow today. So, anyway, the CUDA warp, in my case, it has 32 threads, and each thread is responsible for a completely independent virtual machine, or a Game Boy in the past. Does its own thing, emulates its own CPU, its own I/O, its own RAM. Now, this is one of the details that is not obvious when you start doing something like this, and something that I learned while I was working on the Game Boy, because technically the things that I do at NVIDIA are not related to GPUs. I don't consider myself to be a GPU programmer, a proficient one anyway. So, say we want to run 320 instances. It will be clear in a moment why, specifically 320. Option 1 is to run 320 warps, where one thread marked green is actually doing the work, and the rest of each warp is unoccupied. It just does nothing. I don't care what it does. It just, there's no load there, no program to execute. So this is option 1, and then option 2 is to use 10 warps, but fully occupied. Technically, in both cases, we do have 320 threads that are doing something that we need. So we have these 2 options. Again, I'd like to ask for a show of hands. Who thinks option 1 is better? Better in more performant. So,
for this use case of Linux?
Yeah, for this use case. Yes, for heavily divergent workloads. Okay, who thinks the second option is better? Well, it's 50-50. Well, the first group was right. I wonder if the first group can explain this.
Well, because you earlier said that the warps are meant to handle, the threads are meant to handle the same tasks. And in this case, when you're executing the kernel code, obviously there are going to be different branches. So it makes sense that each individual warp executing a different branch of the code will be faster than just having less warps but more threads that do different things.
Exactly. Yes, that's the right explanation. I would like to add more details though. So
Better cache friendliness and less stack tracing because you don't have to grab back and less overhead.
less overhead. In a way, yes, but I don't think it has a lot to do with caches. So what actually happens under the hood is, say here, we have 32, like CUDA work number 1, 32 instances of a VM, each running its own Linux with something in it, and they are heavily divergent. Long time ago, they diverged so heavily they do not run the same instruction at all. Whenever this happens, the CUDA work stalls. When it stalls, nothing gets executed at all. In the first case, when this 0th thread stalls, there is a hardware CUDA work scheduler in each streaming multiprocessor inside GPU. There's this thing called SM, and it actually has a hardware implemented in hardware scheduler that is well aware that a certain warp is stalled, and it can really quickly switch this warp for something else. And it's really efficient at that. And so it might not be actually that obvious that you should run this unoccupied CUDA warps for heavily divergent workloads, because GPU in hardware can manage this much faster than you do. Okay, so now switching to RAM, now that we have some implementation of the CPU, all by itself, of course, it's not enough. You need to model memory, right? And this memory, in our case, will contain, obviously, a compiled kernel. This is where the instructions that we execute will be loaded from. And then we need this init RD image. I'm going to talk a little about this in a few slides. And then we need DTP. DTP is actually really small. It's like 1 kilobyte. And let me start explaining what from the tail end. So what's DTP? DTP stands for device tree binary, I believe. It's just a format. It comes from a device tree source, which is it's a definition of the machine actually, and it's very important for Linux kernel to have this definition. And the way this works is when you define this machine in a language called DTS, and you can actually you cannot see it. Let me scroll it here. You define a machine here that contains a CPU with one core of type RISC-V. There is a special type of RISC-V, IMA. M stands, by the way, for multiply and divide. We do need this ability for Linux kernel. A stands for atomic support, and then I is just the most basic instruction set in the RISC-V that you have to support in order to call it RISC-V. So this is a fairly minimal implementation of RISC-V that I have here. We need an interrupt controller. We need to define our memory, and then we define a couple of input-output devices. In my case, this is UART. Does anyone know what UART is? Right? Do I need to explain this? This is a serial interface that is basically used for, say, STD in, STD out, even in contemporary servers. Something to use instead of a screen, for example, among many other use cases. And then I also define a network interface here. So this file gets compiled into a binary blob called DTP, and it's so important to Linux kernel that you must put a pointer to DTP in the register A1 of the CPU before the very first instruction of Linux kernel starts executing. It just expects it to be there to understand what is the configuration of the machine and how to work with it. Now, the next question is, what's init-rd? Who knows what init-rd is? Okay. So init-rd stands for initial run disk, which is used to basically bootstrap a standard Linux boot process. Oftentimes you need oftentimes just Linux kernel is not enough. You need some drivers for a file system, for a certain device, in order to be able to mount the actual root file system that you will use while using Linux. It could be, say, a network attached root file system that you are going to boot into. In order to talk to that network attached file system, you need to stand up a network card. In order to do that, you need to store somewhere a driver. And so, in principle, init-rd is just your typical normal root file system, just a very tiny one. Typical size for init-rd is something like 2 to 8 megs. It's ought to fit into RAM and is used by kernel to be able to continue the boot process. Now the final part is input-output. In my case, it's really a simple setup. It's the memory management unit, interrupt controller UART, and the network card. And visually, the way this all connected is going to look something like this. So you have an MMU, and you have a load, say, from memory, some instruction that tries to access memory. This MMU is basically connected to a CPU, and when it sees that someone is about to load, say, with this address, it knows, this MMU, it knows which device is mapped to which range of addresses. One thing that I forgot to put on this slide is obviously RAM. So if you are outside of any of these ranges, then it just goes to your normal memory. But if you are inside one of these ranges, then this write is going to a particular device, and this is how you communicate with all the devices that you have in your system. So after doing all this, I was able to have this simulation, emulation of 64 virtual machines running on my small RTX 3060, and you can see that, can you see it? Oh shit, it doesn't fit. Actually, at each line, you can see they are doubled, obviously, because each line comes from its own VM. So you can see how they all boot more or less at the same time. And if the video would fit on a slide, you will see that each line is prepended with something like VM number 2, VM number 52, 54, etc. So this is how it looked like at certain point of this exercise, that I was able to load a Linux kernel, but I thought, and now what? Like, okay, I can load the kernel, but I want to do something more interesting. And I realized it's done without input-output. Yes, I have defined network card, but I don't actually use it. I'm just loading a Linux kernel, right? So I decided, like, let's make a nice demo. And the way to do this demo, I thought, would be like this. So on the left, we have this GPU that runs some amount of virtual machines, like I just described, with CPU, RAM, input-output devices, etc. I would compile such an image of init-rd that it would include Nginx, because I thought I should go all the way. Like, running Nginx on a GPU is weird enough. I should stop somewhere. And so these are the VMs. And then on CPU, I have this host application that obviously runs this CUDA kernel periodically, like I explained, and then it captures network packets, it massages them, transfers them on GPU, so that each VM on GPU would think that they came from some network, and then react to it. Nginx would react, answer to this packet. I would get this packet back from GPU and inject it back into the network stack on the host. Where these packets would originate from is, of course, from the browser, some web page that is going to talk to each of these VMs in some way. So that's the idea for the final demo that I had. And now let's focus on what this packet vwrite is, what that actually means. So on the way, imagine there is a web page that is doing an HTTP request to some IP address, some port, and we somehow capture this packet, and we want to put this packet into a particular VM. And the way this works is we map each VM to a port on a host. So say VM number 44 is going to be sort of listening. You will understand in a few slides because I'm saying sort of listening on a port 4044. And then VM 128 would listen on a port 4128, etc. So what are the actions that we actually need to do in order for this to work? We need to intercept the packet first. We need to rewrite the destination Ethernet address, otherwise it's just going to be dropped by the Linux kernel because the Ethernet address does not match otherwise. We need to rewrite the destination port to 4000 because this shenanigans of matching VM to a particular port is each VM does not know about this. Each VM is exactly the same. It just listens on the same port 4000, and so we need to change this port so that the other portion of the network stack and Linux kernel would not drop the packet. While we're doing that, we're corrupting packets because the checksums at IP layer, at TCP layer are not going to be to match anymore. So we recalculate the checksum, and then we put the packet into an appropriate VM's receive buffer of the virtual network interface. And this begs the question, how do you actually do this? What it means to put a packet into a receive buffer of a virtual network card. Now, what it actually means is basically a memory copy, except it's kind of hard. This virtual interface has the same sort of queues and rings that Ashok was just talking about. And you don't really have a nice pointer on the host side to at least when you do it like this, when you emulate this, you don't really end up with a nice pointer to each network interface receive buffer. You still just have a pointer to the entire address space, entire RAM of each VM. That's all you have. And so CUDA managed memory is going to help here quite a lot. The way this works is in CUDA you can allocate memory many different ways. The most performant way, and this jives really well with what Ashok says, if you want this to be fast, do it manually. I didn't want this to be fast. I promised this to be about how to think slow. And so, of course, the most performant way is to do it manually. You just do CUDA malloc, your normal CUDA malloc, and if you need to move data, you do it explicitly. However, for lazy programmers, there is another way, which is called CUDA managed malloc, where you depend on the driver to maintain a shadow copy of the memory, GPU memory on CPU, and you can make the CPU copy dirty by simply writing to it, and then the page fault mechanism kicks in, and only this page is going to be updated. So you just don't care. You don't want to say, I just captured a packet that is 200 byte long. I don't want to copy, say, 20 megs, the entirety of 20 megs of my machine from CPU to GPU. I only want to copy 200 bytes, but I don't know where they are. So I don't care. I just say it's CUDA managed memory, and I just write it on CPU. It happens to fall in a particular 4 kilobyte page, and the driver manages the rest. It just migrates this page from CPU to GPU. So whenever you need to do a lot of small writes from CPU to GPU, you can try CUDA managed memory approach. And a small remark here is CUDA managed memory plus TCC mode actually allows you to run everything that I am talking about completely independently at its own pace. So in principle, if you have Linux, more or less recent GPU, you have TCC mode available, you can start the kernel, it can run for hours, no one will kill it, and you can talk to this kernel over managed memory very easily, and that's the way how I would like eventually this to run. Now that we understand how to get packets into a VM, let's take a look at what happens on the way back. And on the way back, we basically go over each VM's TX buffer now, not receive buffer, but transmit buffer. We check whether there is data, whether a network stack for each VM decided to put something into this transmit buffer, and we extract this data. We again massage it according to the same rules. We need to match a VM. We know which VM we have taken the packet from, and so we know into which port to inject this packet on a host system, so that our browser would think that it actually got the answer from somebody on that port. Now, the problem with this entire idea is that I'm only capturing packets, I'm intercepting them. I'm not stopping them from going further. And that's the problem, right? Because my browser here sends a request, because remember, it's doing an HTTP request. HTTP is based on TCP. In order to establish a TCP connection, I first need to exchange some packets. And so that's what the browser is doing. I'm capturing these packets. I'm doing this whole packet rewrite that I was just describing, but also this packet is going to normal Windows network stack. And Windows network stack does not know about all of this. Yeah. It just thinks that no one is going to listen on this port, and so it sends reset, and my browser immediately just says, well, it's not going to work. What's the solution? Well, the solution is just to kill it, to kill these packets, stop them. If I were doing this on Linux as a host system, I would just use something like this for IP tables. But here I had to kill it in a different way. There's this WinDivert driver, essentially a virtual driver that you can use just to instead of IP tables to kill this. This is the part of the whole setup that I was genuinely not interested in. I just wanted to get it going so everything works at this point. So this is where all the fun begins. I thought perhaps naively at this point that I covered all the bases and that it should just go well and with relatively small effort, but I was wrong. I noticed that I just don't receive any packets in Nginx. I set up a breakpoint in the emulator input-output code, and I thankfully see that the Linux kernel does pick up the packet. So something is trying to at least access this memory, so that's a good sign. But still there is a problem. At least the problem is not in the part of the emulator. I would call it a hardware problem in this case. I still emulate hardware, it's all software obviously, but from the VM standpoint, the hardware is good, so to say. Linux kernel observes something in the virtual network interface and tries to read it, but it goes no further. So I need more tooling. I should mention that me talking about this here and me trying to debug it takes disproportionately different amount of time. Right? Every time I need to do even the smallest thing, like even looking up the log of kernel that was just loaded, or looking through Nginx logs, or doing a simple thing as like ls is monumentally slow, because I promised it's going to be slow, and because I forgot to mention I emulated UART, but only on the output side. I didn't have any inputs, because in the beginning I thought, how on earth would I talk to 64 or 500 VMs with a single keyboard anyway? So I didn't implement any code for input, so I wasn't even able to type ls or something like that. And so you just put these commands into init script, reboot the machine, wait until it's booted, and observe the results, think about this, do it again, etc. So one useful thing that I found is buildroot, which is a collection of scripts that you can use to quickly configure and build a kernel and a initRD image. And it contains a lot of build scripts for certain tools and applications that you can include into your initRD image. So using buildroot, I recompile initRD to include this ETH tool, which is really useful when you try to debug something or at Ethernet level. I thought the hardware, as I mentioned, is working, but I still want to get some proof from the VM standpoint that it recognizes these packets as Ethernet packets. And so with some magic options, it's fairly easy to see how many packets it observed. And I was able to confirm that it does recognize them as Ethernet packets. And so the problem was not at hardware, it was not at Ethernet level. Well, actually, wait, this problem was the Ethernet problem, but the ETH tool was not enough to understand the problem. So I recompiled initRD again to include the TCP dump tool. Who here is familiar with TCP dump? Yeah, some people are. It's just a tool that you can use to capture packets at almost any level of the network stack and analyze it and set up a lot of filters on ports, on protocols, etc. And so with this tool, I was able to find.
Where you store TCP dump output? It's UART output or something else?
It's just UART STT out,
Okay,
just reading through the logs. Yeah.
So with TCP dump, I was able to find quite a lame issue that I didn't configure a MAC address correctly for this virtual interface. And so I fixed the packet rewrite and also manually added an ARP entry to match HVM's MAC to an IP address to also avoid ARP traffic. I didn't want to deal with this. I just wanted for a machine to do exactly just talk over the protocol that I'm interested in, which is TCP for this HTTP request. So the init script now looks like this. We configure the IP address on the interface. We set the fixed MAC address, which is the same, just as IP address on each VM. And you know this feeling that I got? It's called, that was it. I thought, okay, this was the problem. Now everything's going to work. But no, I was wrong again. The packet still did not reach Nginx at this point, and this was quick. I realized with TCP dump that now packets are dropped because the checksums are bad, and this was an issue of byte order. So fixing the packet rewrite again. And at this point, of course, again, just as any naive programmer, I thought, okay, this was it. Now it's going to work. And Ethernet layer is fine, IP layer is fine, checksums are good, but no, it's not going to work this time again. I recompiled the kernel again, to include IP table support. Some heavy artillery at this point. And I'm using this tracing capability of IP tables to really understand why the Linux kernel decides to drop the packet. And at this point, I realized that the routing table is empty. And this was the, I decided to include this picture here because I spent so much time with these IP tables, recompiling kernels, recompiling in itherd for such a simple and stupid mistake of just not populating a routing table. Now, I've added this as a last line to the same init script. And this was a small victory at this point because it actually started to work. I was able to do a small test, not a full-blown test with the browser and all that, just to ensure that I can forge a packet and it would reach Nginx, and Nginx would try to answer. So at this point, I just wanted to get this across the finish line, and I needed to create this browser web page, which would access all the VMs. Unfortunately, I don't know how to do this, but ChatGPT was able to help in this case. It's a fairly simple web page, after all. And then some small touches on adding a cron job and HVM to update this index.html file that is going to be served by each Nginx. This index.html would contain the output of the command uptime. You will see in a few moments why is that necessary. And then, of course, a minor Nginx configuration tweaks to actually do what I needed it to do. At this point, I understand this could have been a lot of information. So let me try to summarize what we're looking at. My notebook has an RTX 3070 GPU, which by itself is, by the way, not the most powerful one. It's mobility GPU. It's strangled in the power department to meet the temperature target. This notebook runs Windows, which runs a process, which runs a CUDA kernel periodically, every 100 milliseconds or so, because this is how long it takes to simulate 100,000 instructions. And this CUDA kernel runs some amount of emulator instances, in this case 256 VMs, each emulating a small system containing a single core RISC-V CPU, a small amount of RAM, and some input-output. Now restarted. And then this same Windows application also captures packets, TCP packets that are issued by the browser. It massages those packets, rewrites port numbers, checksums, and all that in order for these packets to be recognizable by each VM as something that it can handle. Each VM contains an instance of Nginx that sees the packet, recognizes it as an HTTP request, answers it, and this web page is 16 by 16 cells, like a grid, each running a timer and periodically sending an HTTP request and showing the content of this uptime for each VM. This is the most visual I thought that could demonstrate that I'm actually running independent virtual machines in huge quantities and all on the same screen. Now some stats. Each VM, as I mentioned, is a single core RISC-V with around 22 megs of RAM, 9 of which, so almost a half, is occupied by the kernel and the itherd, and the rest is actual RAM that can be used by the system. I could fit 320 VMs or so within my notebook, and then at work on a bigger GPU I could fit around more than 1,000 of such VMs. The boot time is around 60 to 100 seconds, I'd say, assuming there is no contention. So obviously if you run a lot of VMs, there is a lot of contention. This hardware scheduler constantly switches warps in and out, and that does make things slower than I. Now, I should mention that there is an opportunity here to optimize it a little. What's the point though? But still, you can notice that kernel image and the initRD image, these regions of memory, are largely read-only. Kernel is not going to rewrite its own code for whatever reason. Similarly with the initRD, with a very small amount of exceptions like logs that can be disabled, or this index HTML that I can do in some other way. It's also largely read-only, and in CUDA it's very much possible to sort of virtualize this 9 megs of memory occupied by kernel and the image together, and store them only once. And so each VM could actually require, say, 13 megs or so instead of 22, at which point we could potentially have like almost 2,000 virtual machines running on a single recent GPU. I didn't do this. Again, this is the part of this exercise where you kind of understand how to do this, and I just, there's nothing visual there anymore. It's just more of the stuff that's even harder to visualize. Talking about efficiency, is it actually efficient by any metric? And surprisingly, the answer is yes, but only if you run a lot of VMs. So like more than 100, say, at least. At this point, GPU actually can have quite a race with CPU in terms of resources needed per VM per instruction, say. So back in Game Boy period, or era, I should say, I did calculate this, and the GPU was around 20 times more efficient, but only if you emulate like more than 10,000 of this Game Boy instances. It's fairly obvious that if you have a choice to emulate one Linux instance or one Game Boy game, it's going to be way more efficient to do it on CPU. Because you don't need to talk to GPU all the time, because CPU obviously is much faster, the pipeline of the CPU is much longer, it's running on a much higher frequency than GPU, so it is going to be faster, but the moment you are going parallel, GPU surprisingly gets ahead. And with that, I think this is all I wanted to tell you about today. If you have any questions, fire away. The mic is there.
Here.
I'm not the one to run this thing around.
Where is the second one?
There.
I'll do that.
Do I have a question?
Thanks for the presentation. Small question about kernel details that you used. What was the version and what was the cost? How much were you disabled to build?
Oh, okay, yeah. So I used 6.11, I believe, or was it 6.8? I think it was 6.8, yes. And the configuration is, you really have to cut everything out. But there is a good reason, because you don't need it. So you just can disable almost everything in the kernel except the VirtIO net driver, among optional parts at least. But other than that, it's just a minimal risk-free configuration for kernel.
Thank you for your presentation. Actually, if I meet the point that it will take a lot of time, is it possible to run, for example, Ubuntu or Debian or any other minified distributor of Linux on GPU?
So I should clear up this question. Do you mean with windowing system, with like graphics, or without?
On GPU, on I guess Linux in TCC mode, so it will be easier.
Yeah, but I mean, still the question is not quite clear. When you say Ubuntu, you should understand that any distribution is basically a Linux kernel, a collection of applications, some configuration,
roughly speaking. So when you say Ubuntu, I am interested to understand whether you mean like with GNOME, say, and
Of course.
like Windows and all that. Okay, because obviously, if you take Ubuntu server, it's essentially the same thing. It's just that it's a bit more than Linux kernel plus init.rd. It's also a root file system that, in principle, I could imagine how to emulate it with just virt.io block, it's called, device. So that way you can emulate virtual disk. And with that, you can really kind of make your distribution that you run on GPU large. So you can include a lot of binaries in there, like GNOME and all this stuff that is in the standard Ubuntu distribution. Now, at this point, you will have something like Ubuntu server with headless mode, without X or Wayland, whatever it's called there. Emulating, so having graphics would necessarily mean emulating GPU on GPU. This sounds like my next phase, but I'm just not there yet.
Yeah, quick question. You mentioned there's a lot of headache and it's very slow in terms of workflow to go back and forth, debug things. Through all this adventure, is there some kind of debugging tooling or something that you found yourself coming back to? Is there some kind of advice you would give if someone is to start this road or like continue in your footsteps? Like, is there some kind of a tool that is a must-have, or like if you were just starting up, you would do first to speed up your workflow in this kind of adventure?
Yeah, the best thing that I think could be done is to, as I said, have a reference implementation on CPU. And first make things work on CPU. The next thing is do implement input path on UART. Because it's nice to have this typing experience when you can interact with the machine. But GPU are notorious for, debugging experience that is not the most pleasant one. Honestly, I won't lie, I just used a lot of prints. Thankfully, in CUDA kernels, you can just do printf, and the driver recognizes it in a special way so that you actually see it on your screen normally. So I did a lot of printfs. I did use a lot of NVIDIA debug tooling, like inside something, I forget. We have actually a developer from NVIDIA in the back there who is working on Inside, but I forgot the product name. It's Inside something where you can set inside
Systems?
maybe systems, yes. Some new generation where you could set a breakpoint in a CUDA code, and it actually shows you the state of the entire work, where each thread is, and what is the state, etc. Pasha, you need to be louder. Inside compute, yes, thank you. Okay.
Just one small question. Did you track how much time all this take from you?
And how many line codes?
Oh,
code lines.
lines of code or time?
No, just time.
Time. Yeah, it was, I'd say, maybe 5 full days if combining the time, but actually it took maybe more like a month, I think. Just, in evenings and maybe at weekends, something like that. In total, I would estimate this to be around 40 to 50 hours in total. Mostly spent in debugging, by the way.
Yep. Find the lost packets.
Yeah. Any more questions?
Yeah. Not a question, but a comment on the way of visualizing this. Could you run something like MapReduce on these multiple cores and compare it to the CPU? So you run with a single core on CPU and then the same task, finding a string in a huge text, split it around these cores. Maybe the result could be comparable.
Do you mean to say, like, I would run the map operation on
this course?
these machines, on
Yes.
VMs? No, I haven't had this idea. I mean, this is just torture at this point, right? I would much rather just implement buff reducing CUDA normally, rather than...
Yeah, obviously.
Yeah.
But, I mean, this could be...
Oh, I see. You mean like
Visualization.
deploy a full-blown cube cluster on this. I have thought about this, yeah. This is actually another direction. Thank you. Yeah, this is...
Sure.
Very good presentation, it's very interesting, but my question doesn't really relate to the running virtual machine on GPU, it more like relates to what you said on the beginning, which was that you mentioned that the running multiple Game Boy instances on the GPU was interested the people who were training models, if I understood correctly, because transferring data between the CPU and the GPU was slow, so if they had to...
Right.
Yeah, so I was wondering, today we have technology where we can, where we have cards, PCI cards, where we can have M.2 slots, multiple, where we can place it on the PCI slot for the CPU to access multiple M.2 drives via PCIe. So I was wondering, why can't the CPU directly access the GPU memory via
It absolutely can. Yes, it's
Yeah.
called unified memory, and you can absolutely do this. The problem is that ideally, of course, you want for CPU to always talk to CPU memory, and you want GPU to always talk to VRAM, to GPU memory. Going across the PCI Express is fast, very fast, but still much slower than going to VRAM, right? There is, in the same vein, if you can avoid talking to the RAM and keep everything in your caches, and this is both true for CPU and GPU, do that. You're going to be even faster. So I'm not saying it's impossible. I'm saying reinforcement learning people noticed that basically the entirety of their learning process was already running on GPU. The only reason they needed some transfers is because they had this really small emulator running really quickly on CPU and giving you this relatively small amount of information, like a 320 by 240 screen of 16 colors. It's nothing. And this state needed to be constantly transferred back and forth. If that state could be kept also on GPU, everything could become much faster in this case.
Yeah. So, well, what about like games where real open world games where assets get loaded, and these assets might be as big as 8K textures, and there are like 5 different types of maps, texture types.
Sure. This wouldn't be applicable in this case. They were talking about much simpler stuff like Game Boy, like Sega, Dendy, other Nintendo consoles. If you want to train your like RAL stuff on something like GTA 5, then of course you have no choice. You will have to actually run probably real GTA 5 that also has a lot of CPU overhead. And, that's the other case.
Yeah, thank you.
Just to add on that,
You can pick up the mic.
just to add on that discussion quickly, and not to take too much time, but yeah, most of the AAA games and the open world games as well, at the moment, do that actually. What you said, basically they try to minimize the bandwidth and stream as fast, stream the data they need, and then the actual rendering, most of the GPU-driven rendering happens on the GPU, so they keep...
Of course, yeah, it's a form of prefetch.
Yeah, it's the last 10 years or so, that's one of the biggest optimizations of most games, to keep most of the memory. Just adding on that discussion.
It's a form of prefetching that would help you to avoid spikes that gamers really do not like. Right. Okay? No more questions? Thank you very much for coming. I hope to see you next
time.